Hello, everyone. My name is Anna Lam, and during my master's, I've had the immense privilege of completing a project entitled How to Form a Gravitational Wave Source, Formation Pathways of Compact Object Mergers from Isolated Massive Binary Stars. Pictured here is LIGO, a gravitational detector that in 2015 detected for the first time two merging black holes that perturbed space-time and released these gravitational waves. Okay, there we go. So gravitational waves are emitted by these extremely dense objects, black holes or neutron stars, and can now be detected by observatories like the one pictured in the previous slide. As these super dense objects merge, they perturb space-time and release these ripples of gravitational waves that we can detect now here on Earth. It is fascinating that we can now kind of observe these exotic objects like black holes, but where did these systems come from? What are the progenitors of these merging black holes and neutron stars? So the biggest stars in our universe, aka massive stars, go through their lives fueled by fusing heavier and heavier elements. And as they reach the end of their lives, they explode and collapse into black holes and neutron stars. Massive stars are really important in our universe. First, they reionize our universe, they chemically enrich our universe, they trigger and trace star formation, and they power a lot of exotic astrophysical phenomena. But our understanding of massive stars is challenged and limited. First of all, massive stars are very rare. The more massive a star, the rarer it is. Secondly, they evolve much faster than their low-mass counterparts. And thirdly, they are hard to observe. Massive stars are usually born in very dense and dusty star-forming regions, so resolving one is very difficult. Another point that makes it really challenging to understand massive stars is that they often come with companions. Observations have proven that massive stars are often born in binaries. As you can see, more than 60% at some point in their lifetime have interacted with a companion. So to understand the lives of massive stars, we need to factor in binary interactions. So what does the life of a binary massive star look like? What does their evolution look like? So first we start with like a bounded massive star pair. One of them will evolve, and as they evolve, these stars like puff up during their lifetime. Some of their mass will reach a point where it will be donated or accreted by their companion. And then that star will have like lost some of its material. That first, more evolved star will go and have an explosive death, aka a supernova. And then the second star will also start to puff up as it grows or lives and might initiate another transfer of mass. This can be unstable or stable. In the unstable scenario, aka a common envelope scenario, sometimes our two stars, or well, now it's a black hole and a star, or a neutron star and a star, might prematurely merge. If they don't prematurely merge, the second will go supernova and get our second black hole or neutron star. And now we have a double compact object, either these two black holes, these two neutron stars, or black hole neutron stars. They will orbit each other and release gravitational energy so that to some certain point they will merge, releasing the gravitational waves we can detect now on Earth. Well, this is just like one scenario. If we go back to the start, we could have an unstable mass transfer episode that begins the evolution of these two star pairs. And they can go on to do all the other intermediate evolutionary stages. So as you can see, there are several formation pathways even within this isolated binary evolution paradigm. One exciting thing about this astrophysical scenario is that the gravitational waves that we detect here on Earth today can be from binary stars very early in our universe. Once they form two black holes, two neutron stars, it can take on the order of giga-years for these two compact objects to merge and be detected on Earth. So using these gravitational wave signals from these mergers, we can kind of trace massive star evolution across cosmic history. So now I pointed out previously a specific formation pathway or dance that these two stars can do. However, the landscape of binary evolution is very vast, and the scenario I described where you get two merging black holes is only one of many different evolutionary outcomes these two massive stars can undergo. So what about all the other pathways and all the other outcomes, and how do we as researchers get a hold of this vast landscape? So what I use is population synthesis simulations. I use a code called Compass to essentially evolve many, many, many star pairs, like on the order of billions. So I essentially evolve them, forward model them, and get an output where like a fraction of these systems will become the things we can observe here on Earth today. And this is really important because we can kind of simulate this population, get this output, and compare it to the detections we see today to kind of get an idea of how close or far we are to understanding the physics that govern this evolution. Another strength of this approach is that it's very cheap computationally. Also, with this approach, I can study different models of what we understand for different physics that govern binary stellar evolution. The limits of this approach, however, is that each of these points are laden with model uncertainties. A big challenge I've tackled in the field of binary population synthesis simulations is to kind of visualize and quantify what's happening to this like immense population. This is a Sankey diagram, and as you can see here, this leftermost side is this is 53 billion star pairs, and I can kind of track all of their lives comprehensively. As you can see, half of them never interact before forming the first black hole, or one of them going supernova. And the majority of these will be disrupted, so they are no longer valid gravitational wave sources. A third of them will transfer mass, either stably or unstably. Obviously, in the unstable scenarios, some of these stars might merge as stars and not black holes. And if they survive that and survive a second supernova event, where you can get your two compact objects, a fraction of them will merge if they are close enough together. And as you can see, these mergers represent a very small fraction of our initial population. So now the question I wanted to ask is, can we measure the importance of all of these other intermediate evolutionary stages in yielding potential gravitational wave sources to better constrain our binary stellar evolution theories? So in order to do this, I focus on one formation pathway at a time. Here's one where we have our two stars. They'll stably mass transfer. One goes supernova, we get our first black hole. Then they'll undergo like an unstable common envelope scenario. The second one goes supernova, and we'll have our merging black holes or neutron stars. As you can see, I've kind of decomposed this pathway into a series of evolutionary stages or factors. And by doing this, as you can see here, each evolutionary stage or intermediate evolutionary stage is represented by these colorful lines. And I can essentially kind of calculate and quantify how many systems like survive or pass through each evolutionary stage. And as you can see, across different models, which is the x-axis, these stages have very varying impacts. For example, I can point out that now the common envelope scenario and surviving that first supernova event are huge bottlenecks for this specific formation channel, but it's model dependent, as you can see. We can also focus on one evolutionary stage, such as the second supernova event, and we can find some interesting things. For example, you would assume that the supernova physics that I test would have the biggest impact on changing this factor, but instead it's the mass transfer and common envelope assumptions that impact whether a binary survives this stage or not. And this is mainly due to some like binary tightening that happens in these processes. So these things get closer together, so they might not be disrupted by a recoil kick during the supernova. So studies like this present a way to quantify just how much we don't know about binary stellar evolution and what we might want to focus on best to get closer to understanding it. They are important first steps, but what about my next steps? So out of this work, I am happily trying to publish open source code and tools for visualizing and quantifying population simulation outputs. And I am also hoping to present my results in a paper. And with that, I'd like to conclude with some main takeaways. So gravitational waves emitted from merging compact objects are a window that lets us understand the lives and deaths of massive binary stars. There's a vast landscape of outcomes and stages of this evolution. And a first step to tackling the uncertainties in this is to focus on the various pathways and intermediate stages. And this is particularly pertinent because we are having future detectors and observing runs that will, greatly increase the number of detected mergers. But of course, this is heavily dependent on continued funding of science. So please raise awareness about the importance of funding scientific discoveries. And with that, I would like to end with a huge thank you to many people who have supported me on my journey. My research advisor, Flor Bruckharden, my mentors, Jared Goldberg and Akasha Cruz, my research group and my collaborators, Jillian Alley and the CUNY MS in Astrophysics program, my peers, the Simons Foundation, of course, and my friends and family. Thank you. Happy to take questions.
Okay, I am an observationalist, and I'm interested in looking at stars. You've noted that some points in this pathway are kind of more key than others. Where should I be looking if I wanted to find these progenitor sources, like along the evolutionary stages?
So yeah, a big part of my work that I didn't really dive into is that in population synthesis simulations, especially of these massive stars, we kind of focus on that final merger stage. And I kind of showed that that is a very rare outcome of these massive binary stars. These are field stars, so we don't even account for like the environment they're in and whatnot. So that is exactly it. I kind of want to use these other stages that we can kind of quantify, like mass transferring systems might be difficult, but like runaway stars or X-ray binaries, and kind of like use those observations to constrain these pop-synth simulations. Because, 53 billion stars, but only like 0.3% are the things that we are observing with gravitational waves and then using to constrain all of this. So, yeah. Thanks. Yeah.
Amazing work.
Yeah.
So I guess my question is, what if there are like other stars that are much smaller and just like are also evolving next? And do you expect that to have a really big effect, or is this basically like if you have two such big stars, like will that affect it?
Yeah. So I don't think we're at the state where we account for other things around them. These are isolated stars, so we don't even consider their environment. So essentially, it's just the gravitational attraction between these two bodies. But one interesting fact is that I think there's some papers that suggest that massive stars are even like more likely to be born in triples or in multiples. But then you still have the inner binary that dominates most of the evolution. But yeah, not yet. We don't even have, I think, a great handle on just the two bodies. Yeah. Mordecai, and then Leonis.
So you mentioned two out of several observable outcomes, runaway stars and final mergers. Can you compare either of those with existing knowledge of frequency of these? That is, can you constrain what fraction of binary mergers might form through this channel, what fraction of runaway stars might form through this channel rather than, say, through subcluster merging like Brooke-Pollack has been showing?
Yeah, no, absolutely. I didn't kind of note that this is just like one formation channel of these mergers. You, of course, have things in globular clusters, AGN disks, which also have or are really efficient at forming these merging black holes or other compact objects such as neutron stars. So I haven't thought much about putting these isolated binaries in comparison with other formation channels, but that is something very important to note. I think my interest is more understanding the stars and how they interact throughout their lifetime. So this isolated scenario is yeah, where I have most of my focus in. Thank you.
Oh, hi. This might be mirroring like an earlier question, but if you're assuming that massive stars are forming earlier in their cloud, does that impact the simulations you were running? Like I think earlier in the slide you mentioned that they might be forming as the
In
cloud
very
collapses,
dense-
but what happens if they're forming later than some smaller stars?
So in our PopSyn simulations, we start them off as just zero-age main sequence stars. So they're just starting out their lives as, with hydrogen burning. So I haven't really. Well, one thing I am interested in doing is that I can do this across different metallicities, so I can kind of look at maybe a redshift evolution of these massive binary stars. Maybe that's a stretch because, yeah, but that's where I'm thinking with trying to understand how to place this evolution in the history of the universe. Yeah.
Cool, thank you.
Thank you.